All right, so we're going to talk a bit about dichotomous data and dichotomous outcomes. We keep seeing this word over and over and over again, but we really haven't had a chance yet to really dive into what it is and what we do with this information. So this will be a very, very, very basic overview of dichotomous data, dichotomous outcome, just enough to give you a grasp of what we're talking about, okay? All right, so what are dichotomous outcomes? First and foremost, let's just talk about what does dichotomous mean. When we see dichotomous variables or dichotomous data, we're stating the fact that it can only fit into one or two categories. So, similar to nominal, however, nominal, while it is still categories, it can be multiple categories. With dichotomous data or dichotomous variables, they can literally only fit into one of two categories. So examples of dichotomous outcomes could be alive or dead, disease or no disease, pregnant or pregnant. Okay? Because it can only fit into two categories, the outcomes are expressed as the chance of being in a group of only one of two possible outcomes or one or two possible states. So with dichotomous outcomes, we use effect measures to determine or to compare two groups and to determine the outcome. Those include risk ratio, also known as relative risk, odds ratio, which we'll go into further for all of these, and then absolute risk reduction. We always use confidence intervals when we're using effect measures because the effect measures that we determine are only estimates. So a confidence interval should always be used. Now, why do we use dichotomous data and dichotomous outcomes? Well, first and foremost, it's a common measure of treatment. And we need to know if there is an effect and how meaningful that effect is. So this is a great way to do it. We determine the number of bad outcomes of disease or the number of bad outcomes of the exposed group to those without the disease or those not treated or those not exposed. So I'm just giving you multiple ways you may see the information. So an example could be considered 20% of a control group developed bad outcomes compared to 12% of those who were treated. Generally, we express the effect measures in percentages. We're going to come back to that example at the very end, but first, let's take a look at the formulas that we use. Some of this you've seen as far as control and experimental, and you've seen the abbreviations for the effect measures: relative risk reduction, absolute risk reduction, and the number needed to treat. Okay, but let's quickly go over what those definitions mean. So you have a control group and you have an experimental group or a non-control group. And the experimental event rate is the measure of how often a particular statistical event, like death, so if we were measuring mortality, so how often a particular statistical event occurs within the experimental group. And the control event rate is essentially the same as the experimental event rate, except that it measures the sign or the statistical event of the control group. So we would ask the same question. How often does a particular statistical event, such as death or an adverse event or a response to a drug, occurs within the control group? Now let's look at the effect measures. We have relative risk reduction, and absolute risk reduction. Relative risk, which is also considered risk ratio, is the risk or the risk ratio of something happening when you compare the odds for two groups against each other. So if you had two groups, one group had very close family members whom has a particular disease, while the other group does not have any close relatives of a particular disease. The group with close family members would be more likely to develop that disease than the group who does not have close family members or close relatives who have that disease. And we generally, again, would state that relative risk or the risk ratio in percentage. So we would say the relative risk is 10%, is that you're 10% more likely to develop that disease because there are close relatives who do have that disease. Okay, but you'll also see it written a few different ways, like X times more likely, such as 10 times more likely. And although relative risk does provide some information about risk, it doesn't actually tell you the actual odds of something happening, but rather the absolute risk does. Okay? Now let's take a look at relative risk reduction. So relative risk reduction is how much risk is reduced in an experimental group compared to the control group. Okay, so for example, let's say we were looking at an experiment for any disease, right? And we were looking at what we have as standard treatment, and we wanted to compare a new treatment or a new drug. If 70% of the control group died and 35% of the experimental group died, then the relative risk reduction for the new group looking at that new drug agent would be technically 50% based on the formula that we have here. So in other words, the death rate in the experimental group is half that of the control group. Okay, so I'll say that again. If 70% of the control group died and 35% of the experimental group died, the relative risk reduction using the new drug or the new therapy would be 50%. So that would mean that the death rate in the experimental group is half that of the control group. And again, this is all based on the formulas that you see here listed, but we will go over this because, as you can see, it's kind of in terms of ABCD, and I'll explain why. Now let's talk about absolute risk reduction. Absolute risk reduction is the risk of something happening or the odds of it taking place. So the absolute risk of something happening is the odds that it's happening over a period of time. So, using the same example, if you're looking at just a particular group of individuals, we could say we could just use a particular group of people. So we have a particular group of people, and we say they have an absolute risk of 15% of developing a disease in their lifetime. We'll use breast cancer because that's very common one. So if we just focused on women in a particular country, we would say there's an absolute risk of 15% of developing breast cancer in a lifetime. And there is an actual statistic for that can be looked up. Those things have been looked at and determined. So that would mean that out of every 100 women, about 15 will develop the disease at some point in their lifetime. Absolute risk is different from relative risk because we're looking at where two groups of people are compared. So, for example, smokers might be 25% more likely to get breast cancers than non-smokers, meaning a relative risk increase of 25%. Number needed to treat, we are going to come back to because I want to go over how to calculate the effect measures. So you've seen this section from our CAP review. This is what we're going to be referring to. We have an outcome measure, which we could consider mortality, and then we're going to look at the control event rate and the experimental event rate, absolute risk reduction, relative risk reduction, and then number needed to treat, and then, of course, a confidence interval, because we always use a confidence interval. This is the ABCD that I was explaining to you that we would come to. This is a very basic overview. This is not mine. I did pull this, so this will be cited. But here's a very basic overview of how we use this information. You have an exposed group. You have a non-exposed group. Yes and no. We take the information from which or the data, and we put it into this is a very basic table, okay? And then we calculate the information for control event rate, experimental event rate. Once we have those two, that information helps us determine the effect measures, including the number needed to treat, because we have to have a number needed to treat. Again, I'm going to come back to the number needed to treat. Okay, so let's put the numbers into place. We've determined what our control event rate based off the exposed and non-exposed, and we've determined what our experimental event rate is. From here, we can determine that based on the information provided for CER and EER, we know that the relative risk would be 0.8, making the relative risk reduction 0.2 or 20%, because remember we express it in percentages. Now, the absolute risk reduction would only be 0.002 or 0.2%. So that would mean that in order for us to see an effect, we would need to treat 500 patients. Okay? Now, we're going to explain this in a little different way. Let's try looking at just percentages. But here's that example that I wanted to come back to. Let's say you have a randomized control study looking at adults with Lyme disease. The study found that 20% of the control group developed bad outcomes while the treatment group was 12%. You have your control event rate of 20% and your experimental event rate of 12%. From there, and because that information is provided, you're able to again calculate your relative risk, your relative risk reduction, and your absolute risk reduction. So let's start with the absolute risk reduction, which we know is also the risk difference. If we take the 20% and the 12%, we know that looking at the formula, absolute risk reduction is control event rate minus experimental event rate. So that's 20 minus 12. That would give us 8%. That means that if 100 adults were treated, 8 would be prevented from developing bad outcomes. Or another way to look at it is that if we calculated the number needed to treat with that, if 8 adults out of the 100 benefit, or that we would say if 8 adults out of 100 benefit from the treatment, then the number needed to treat for one person to benefit would be about 13, because using the number needed to treat, because we now know the absolute risk reduction would be 1 divided by absolute risk reduction. We would need to treat 13 individuals in order for one person to benefit. Okay? Because the number needed to treat for one person to benefit is based off the 1 divided by absolute risk reduction, which came out to 12.5. Now let's look at relative risk. We know that relative risk, the equation is experimental event rate divided by control event rate. So in this case, the relative risk would be 12 divided by 20. That's 0.6%. And relative risk, when we look at relative risk, we're saying what is the relative risk of a bad outcome in a group given intervention. Okay? And we're looking at that as a proportional measure, estimating the size of effective treatment compared with the intervention or no intervention. No intervention, okay? And the proportion of bad outcomes in the intervention group is divided by the proportion of bad outcomes in the control group. Now, if we have a treatment of relative risk that's greater than 1, the risk of bad outcomes is increased by the treatment. So when relative risk is less than 1, the risk of bad outcomes are decreased, meaning that the treatment is likely to be good. Okay. Now let's take a quick look at relative risk reduction. Relative risk reduction tells you how much the treatment reduced the risk of bad outcomes relative to the control group who did not have the treatment. and using the formula provided for relative risk reduction, that's how we would determine it. It's also our most common.